This is part 2 of 4 chemical reactions video experiments. In this video, we'll be studying decomposition reactions and acid-base reactions, also known as neutralization reactions. And there are many examples of decomposition reactions. We're only going to look at 2 types. First, the decomposition of a metal bicarbonate, and secondly, the decomposition of a metal carbonate. The decomposition of metal bicarbonates. A metal hydrogen carbonate, which is the same as a metal bicarbonate, will decompose on heating. For example, baking soda, NaHCO3, is a natural fire extinguisher. Heat from a fire will decompose baking soda, releasing water and carbon dioxide gas. And since carbon dioxide is denser than air and is non-flammable, it smothers the flame by excluding the oxygen. The decomposition of a metal bicarbonate yields a metal carbonate, water, and carbon dioxide. Let's take a look at the decomposition of a metal bicarbonate. The test tube on the left contains sodium bicarbonate, commonly known as baking soda. In the test tube on the right, I'm adding a saturated solution of calcium hydroxide called lime water. Calcium hydroxide is a strong base, and it's used to detect carbon dioxide. When the sodium bicarbonate is heated, it liberates carbon dioxide gas, and that carbon dioxide gas is being bubbled into the solution of lime water. Now, carbon dioxide reacts chemically with calcium hydroxide, precipitating calcium carbonate, CaCO3. Calcium carbonate is essentially limestone, and it's insoluble in water. And after some time, you can also see the buildup of water condensing in the top of the test tube on the left. And so we see that the decomposition of a metal carbonate releases carbon dioxide gas and water. And what's left in the test tube on the left, that white solid, is no longer going to be sodium bicarbonate, but will be a metal carbonate, in this case, sodium carbonate, Na2CO3. So here's the chemical equation. 2NaHCO3 liberates 1 molecule of carbon dioxide, 1 molecule of water, and the metal carbonate, in this case sodium carbonate. So you need to remember that 2 bicarbonate ions produce 1 carbon dioxide molecule, 1 water molecule, and 1 carbonate ion. Let's get some practice. This is magnesium bicarbonate. Magnesium bicarbonate is, when heated, will decompose into carbon dioxide and water and the metal carbonate, in this case magnesium carbonate. Now this one's easy to balance because magnesium is in group 2A, its charge is +2, and carbonate is -2, so they combine 1 to 1, and that equation is balanced. How about calcium bicarbonate? When heated, it decomposes, producing carbon dioxide and water, and the metal carbonate, in this case calcium carbonate. And since calcium and magnesium are in the same group, they both have a charge of +2, it balances the same as the magnesium bicarbonate decomposition. Calcium bicarbonate is the major form of water hardness. When heated, it deposits as a white scale, and you might see this in the bottom of a kettle, and we see it industrially in boilers. Alright, the last decomposition reaction we want to look at is that of the decomposition of a metal carbonate. So after a metal bicarbonate decomposes into a metal carbonate, the metal carbonate itself can be further decomposed with prolonged heating into a metal oxide and carbon dioxide. So for example, limestone is largely made of calcium carbonate. Limestone is mined, it's crushed and heated in kilns, these are high temperature furnaces, to produce carbon dioxide and a white powder known as calcium oxide, often called lime or quicklime or even dry lime. Note in the reaction that each carbonate ion produces one molecule of CO2 and one oxide O-2 anion. Now, lime is a strong base and it's a component of cement and mortar. All right, your turn. Magnesium carbonate is a secondary component of limestone. Write a balanced equation for the decomposition of magnesium carbonate. We'd write magnesium carbonate decomposes into carbon dioxide and the metal oxide, MgO. Let's look at one more decomposition reaction. This will be the decomposition of hydrogen peroxide, H2O2. Oxygen is in group 6A and it is most stable when it has an oxidation state of -2. Hydrogen peroxide is an unstable compound in which oxygen has an oxidation state of -1. And so peroxide decomposes as shown. It decomposes into water and oxygen. Now this reaction is accelerated in the presence of potassium iodide, and the addition of some liquid dish detergent will add a little drama to the demonstration that we're about to see. Just a word of caution, 30% hydrogen peroxide will cause immediate and permanent eye damage, so safety glasses are an absolute must when doing this experiment. The last portion of chemical reactions 2 deals with acid-base or neutralization reactions. The fifth type of chemical reaction we're looking at is neutralization reactions of acids and bases, such as hydrochloric acid reacting with sodium hydroxide to produce water and a salt, in this case sodium chloride salt. So in neutralization reactions, an acid and a base react to produce water and an ionic compound, which is a salt. Now what's an acid? Well, most acids have hydrogen covalently bonded to a nonmetal, as for example in hydrogen chloride, hydrogen sulfide, or hydrogen nitrate we call nitric acid. The bottom line is that acids produce hydrogen ion in water. Now many bases have a metal cation ionically bonded to a hydroxide ion. For example, sodium hydroxide, potassium hydroxide, calcium hydroxide, aluminum hydroxide. Not all fit this description, but the bottom line is that bases produce hydroxide ion in water. Let's look at some familiar examples of acids and bases. Acetic acid, CH3COOH. A 5% solution of acetic acid is what we call vinegar. Sulfuric acid, H2SO4. A 36% solution of sulfuric acid in water is the electrolyte in the lead-acid automobile battery. Phosphoric acid, H3PO4, is sold as rust remover for cleaning rust spots off a car, and small quantities are added to carbonated beverages to give the flavor of colas or root beer. Nitric acid, HNO3, is quite an aggressive acid, and it's one of the main components of acid rain produced by NOx from automobiles. Hydrochloric acid, HCl, is often used to clean the lime out of stains from mortar or brickwork. And carbonic acid, H2CO3, forms whenever carbon dioxide is dissolved in water, as in the case of carbonated beverages. Now, how about some bases? Sodium hydroxide, NaOH, is commonly referred to as lye. It's the main component of Drano, which combines sodium hydroxide and aluminum to dissolve grease in a drain. Also easy off oven cleaner. contains sodium hydroxide. These are degreasers. Magnesium hydroxide is a little milder base, and it's what we would call milk of magnesia for neutralizing acid indigestion. Calcium hydroxide, CaOH taken twice, is commonly called lime, and it's one of the binding agents in mortar and cement. Ammonia, although it doesn't have the typical formula of a metal bonded to hydroxide, it is a moderate base, and in water it produces hydroxide ion. A 5% solution of ammonia is called Windex. It's a degreaser and a glass cleaner. Sodium carbonate, another non-hydroxide base, does produce hydroxide in water. It's used in detergents and as a degreaser. It's commonly called washing soda. The last example I have here is sodium bicarbonate, which is a very weak base and is commonly called baking soda. The general form of an acid-base neutralization equation is as follows. A generic acid, HX, reacts with a generic base, BOH. And the hydrogen ion from the acid combines with the hydroxide ion from the base to produce a water molecule, HOH, or more properly, H2O. Then the cation from the base, in this case B, reacts with the anion X from the acid to produce the salt, BX. And again, our most familiar example, HCl and NaOH produce water and sodium chloride. Let's get some practice. Here we have potassium hydroxide and nitric acid. They are both mono-reacting. The KOH is a mono base and nitric acid is monoacidic, and so they react in a 1-to-1 ratio producing water and potassium nitrate. The nice thing about acid-base reactions is that if you simply balance so that hydrogens and hydroxides are combined in equal ratios, the salts always work out properly. Barium hydroxide is dibasic and sulfuric acid is diacidic, so we have two hydroxides combining with two hydrogen ions producing 2H2O, and then the salt is barium sulfate, and that is balanced. Phosphoric acid is triacidic. Sodium hydroxide is monobasic. We're going to need three hydroxides to combine with the three acid hydrogen ions from phosphoric acid producing 3H2O, and the salt then will be sodium phosphate, Na3PO4. Hydrogen chloride is monoacidic and iron 3 hydroxide is tribasic. So we're going to need three HCl molecules to give three hydrogen ions to neutralize three hydroxide ions to produce 3H2O, and the salt will be FeCl3, and this is properly balanced. And finally, carbonic acid is diacidic, calcium hydroxide is dibasic. They'll react in equal quantities producing 2H2O, and the salt, in this case, is calcium carbonate, which happens to be an insoluble salt. By way of an acid-base reaction, let's look at the decomposition of sodium carbonate again. There's a lot more going on here than just decomposition. In the first step, sodium bicarbonate decomposes into sodium carbonate, carbon dioxide, and water. In the second step, lime water, calcium hydroxide, that was put into the test tube, reacts with the CO2 gas, precipitating calcium carbonate, solid. Forms a turbidity. Precipitation reactions are the subject of our next chemical reactions video. Now, carbon dioxide, like many other non-metal oxides, is acidic, and it reacts with water to produce carbonic acid. In the fourth step, calcium carbonate, the precipitate, is a base, and carbonic acid is an acid. So this fourth step is a neutralization reaction forming calcium bicarbonate. Now, calcium bicarbonate is in solution. It's soluble. In fact, it doesn't even exist as a solid. It can only exist in solution. Things to look for. We've added this universal indicator to the test tube. Now, universal indicator is a mixture of three different indicators, and it allows us to estimate the pH based on the color. Anywhere between pH 0 and 4, it looks the same. It's red. anywhere between pH 10 and 14. It looks the same. It's purple, but we can estimate between 10 and 4. And you'll see at the beginning that when we add the indicator, the solution turns purple because calcium hydroxide is a base, so its pH is 10 or greater. And you'll see gradually, as carbon dioxide is bubbled into the solution, the color switches from purple to blue to green, ultimately to start to see a hint of yellow as more and more acid is being added and the neutralization progresses. Let's take a look at this video. In the vertically mounted test tube, I have a clear, colorless solution of calcium hydroxide called lime water. In the test tube that's mounted on an angle, I have a white, solid sodium bicarbonate. You'll notice also it's got a blue-green hint to it. That's a couple drops of universal indicator I've put in, and that indicates that sodium bicarbonate is in fact a weak base. When I start to heat this, the carbon dioxide gas will be liberated and react with the calcium hydroxide in the test tube that it's bubbling into. I'm going to add some universal indicator here. The solution will turn purple because calcium hydroxide is a base. But it also went cloudy, and that's not from the indicator. It's from the carbon dioxide gas reacting with the calcium hydroxide and actually precipitating calcium carbonate. Now I've sped this up a bit, and if you watch, you'll notice the color changing from purple to blue to green and ultimately a hint of yellow as the calcium carbonate is being neutralized by the acidic carbonic acid. But also you see the calcium carbonate dissolve, forming soluble calcium bicarbonate. So this is an acid-base reaction. So this is the end of part 2 of the chemical reactions video experiments. You'll need to see the written lab procedure for additional content that is not in this video, and for the lab report requirements, including equations you need to balance and questions to answer. There are also a few short video clips related to decomposition and acid-base reactions that you should watch. The videos or their hyperlinks are posted on Blackboard. In addition to providing some good learning, some of them are quite entertaining. Thanks for watching.